Hi guys, starting chapter 16 today. We're going to talk all about fluids and just some different rules that kind of go along with fluids in chapter 16. For section A, let's figure out what a fluid is first of all. I don't know about you, but when I hear fluid, I automatically think of a liquid, okay? But a fluid is actually any substance that can flow, and so it includes liquids and gases, okay? So our laws and our rules that we talk about in this chapter are going to apply to liquids and liquids and gases. Okay, one of the things we talk about with both gases and liquids is viscosity. And it's basically a measurement of its resistance to flowing. It's easier to kind of visualize this with liquids, okay? So if you have a jar of honey and you have a cup of water, obviously the honey is a lot thicker than the water, okay? It's more viscous, it has a higher viscosity. It's going to take longer to flow than the water does. But that's true with gases also. You have different thicknesses of gases, but it's just easier to visualize with liquids. Fluids also exert pressure, okay? And pressure is basically the amount of force for a given area. It is the calculation right there, force divided by area, okay? And basically what that means is the smaller you make the area, the sharper you make something, the bigger the pressure is going to be. So if I have a force of 10 and an area of 5, I'm just making things up. If I have an area of 5, my pressure is only going to be 2. But if I decrease the area to 1, 10 divided by 1 is 10. So I've now increased the pressure, okay? And so that's why you can't really stab yourself with your finger. It's too big of an area. But if you have like a needle for a vaccine or something, it's a much smaller area, same amount of force, it can exert more pressure and actually pierce the skin, okay? Pressure is measured in something called pascals. It's named after this guy with the coolest name in science, Blaise Pascal. Anyway, it's basically newtons per meter squared, and that's just shortened into PA for Pascal, okay? All right, so now let's relate pressure to things that we experience all the time, air and water, okay? There is a lot of air pushing down on us. The atmospheric pressure, depending on our elevation, will determine how much air is actually above us. At sea level, that's considered 101.3 kilopascal. We simplify that and refer to that as 1 atmosphere of pressure, but there's actually mass to it, okay? The column of air that's above you is actually pushing down on us, okay? But the fluid in our bodies is kind of pushing out, and so it's very balanced. Sometimes this becomes unbalanced, and you notice that when you drive up into the mountains. So if we look at this dude down here at sea level, he's got all of this air above him, okay? But this dude up here in the mountains has less air pushing down on him, okay? So this guy is going to experience much higher air pressure than this guy, okay? So air pressure decreases with altitude, and this is what causes your ears to pop. The inside of your ears is separate from the outside of your ears. It's separated by your eardrum. It's a membrane that kind of closes off the inner ear. The pressure inside is stabilized to the pressure outside. It's totally equal. When you go up a mountain, because there's less pressure outside, the higher pressure inside your ear is pushing on your eardrums, and it's very uncomfortable. You actually have a little tube that leads from your inner ear down to your like sinuses, kind of in the back of your throat area. And so when your ears pop, that's a release of that higher pressure inside. Now it's stabilized for high altitude, okay? So it's lower pressure inside, lower pressure outside, balanced, feels good. You drive back down the mountain to this guy with the higher pressure. Now all of a sudden there's high pressure outside of your ear, low pressure inside. That high pressure is going to push inside, so your ears pop again, okay? You can notice this with things like water bottles and chip bags when you drive up into the mountains and home. You'll notice an expansion, okay? High pressure is always going towards low pressure, though. You also notice this in the water. The deeper you go in the water, the more mass of water is above you, okay? So if you have a swimming pool and you're like right here, you only have that much water above you. If you dive all the way down to the bottom, you have much more water on you. So water pressure increases with depth. If you've ever dove down and tried to touch the drain before, you might actually feel that pressure on your ears. If you're wearing goggles, you'll notice the goggles are actually getting pushed to your face more because of that increased water pressure. Okay. All right. So we get some kind of rules here. They're called principles that have to do with some of these fluid dynamics here. Okay. So Pascal's principle is our first one, and it's kind of a simple one. Basically, if you exert a pressure on a confined fluid, whether it's a liquid or a gas, okay, but really we kind of think of this one more as a gas. If you squeeze it, the pressure is exerted on all parts of the fluid, okay? So think about it. If I'm squeezing a balloon, the pressure is not just being exerted where my hands are. The pressure is being exerted to every bit of the gas inside of that balloon, okay? That's Pascal's principle, also named after Blaise Pascal, okay? All right, let's talk about buoyancy for a minute before we get to our next principle, okay? Buoyancy is related to sinking and floating. We're going to talk about that as well. There's a force that basically counteracts gravity, and you've noticed this when you get into the swimming pool, okay? The buoyant force is an upward force that is related to the displacement of fluid, okay? This is why you can do chicken fights so easily. This is why people are lighter in water. If you were to stand on a scale in your swimming pool, you would actually weigh less because this buoyant force is countering the pull of gravity a little bit, okay? And so it decreases your weight. Your mass is the same, but it'll decrease your weight. Buoyancy itself is caused by that buoyant force, and that's basically just a tendency for objects to float. Not everything floats though, okay? Some things, if the buoyant force isn't big enough, okay, so we relate this buoyant force to the amount of fluid displaced. If you drop an object into a bathtub, it's going to, like imagine a very full bathtub and then you get into it, the water's going to overflow, right? So an object will displace a certain amount of water, okay? If the weight of the object is more than the weight of the fluid displaced, the object's going to sink. If the weight of the object is less than the weight of the fluid displaced, then the object is going to float, okay? We'll do some examples of that in class. So now we get to Archimedes' principle that has everything to do with buoyancy, okay? So Archimedes' principle tells us that the amount of the displaced fluid is, first of all, well, this is the principle down here, but this is important to know. Oh, come on. The amount of displaced fluid is equal to the volume of the object, okay? So if I have a funky shaped object, it's difficult to determine the volume of it, okay? Let's say I have a hammer. I can't do length times width. There's all kinds of, I just can't really measure the volume of this. But if I put this in a beaker of water and I determine how much higher the water level goes, that's going to tell me how much water was displaced by this. That's going to equal the volume of this object, okay? The weight of that displaced fluid is going to be equal to the buoyant force acting on this object, okay? So however much fluid is displaced, with Archimedes' principle, we're really talking about water. So however much water is displaced, the weight of that is equal to the buoyant force, okay? Again, if the object weighs more than that buoyant force, it will sink. If that object weighs less than that buoyant force or the amount of fluid displaced, it will float, okay? Some things sink and float because of density also. And if you look at page, what is it? Page 379, you can see a density tube in the book there. There's a little bit of a picture one right there. We can calculate density as mass divided by volume. So however much mass you have divided by the amount of space it takes up, that's going to give you an object's density. And density is how much matter is crammed into the object, okay? Water has a known density of 1 gram per cubic centimeter, okay? Or 1 gram per milliliter. That's a known quantity, and we use it to compare things, okay? So if I put a substance into water that has a density higher than 1 gram per cubic centimeter, I know it's going to sink. Any substance will sink when it's compared to something with a lower density, okay? So if I'm comparing this blue liquid and this green liquid, I would say that the blue liquid, this one right here, is more dense than this green one up on top, okay? The green one is actually floating on that blue one, okay? But I have another liquid here. So that orange one is even more dense than the blue one. The blue one is floating on the orange liquid, but it sank when compared to the green liquid, okay? So this would be the lowest density of the fluids in this example, and this would be the most dense of the fluids. But then you've got some objects too, okay? I don't know what this is in the middle right here, but that tells me that the density of that object is more than both of these liquids because it sank through both of those liquids, but it's less than the orange liquid because it's floating above that, okay? So a substance will float if it's less dense to the substance, the fluid that it's being compared to, okay? So let's talk about a ship, okay? If you think of just the metal, so a huge ship, boom, big, pipe, and, this is like the steam pipe, and here's the wheel, I don't know, little porthole and whatnot. All right, big ship, not so much of an artist, okay? If I just take the density of that metal, that metal is going to be way more dense than water, and it's going to sink. But the reason a ship floats is because you're actually taking the density of the entire hull of the ship, okay? And really it's, if the water goes up to that level, it would be this portion that's displacing the water. The air and the metal now together will have a density that's lower than the density of water. And so that's why a ship can float. So the shape of the bottom of the boat is very important because you want all that air inside of it, okay? I drew too much. We get this thing known as natural buoyancy, and that's kind of the middle ground between sinking and floating. Neutral, I said natural, neutral is neither sinking or floating. So neutral buoyancy results with equal densities. And we see this in nature with fish. They have a swim bladder, and so they will change their density. If they want to swim deeper, they will increase their density, less air in the swim bladder so that they can dive down more. If they want to go up higher, they'll increase the amount of gas in that swim bladder, decreasing their density so they go higher. Same with submarines. They have these big, tanks of air basically that they can empty out and fill up if they want to rise or lower, sink or float, okay? If you put an object in a liquid and it kind of hovers, that means its density is super close to the density of the liquid that it's in. That's also an example of neutral buoyancy, okay? All right, that's all I've got.